Hey, Math 30-2s. Today we're going to look at modeling data using exponential and logarithmic functions. So, some real-life applications. Analyzing the data. Simone, a medical research scientist, is investigating a new bacteria culture which could help strengthen a person's immune system. She isolates 50 cells and records the growth in the number of cells over a period of 5 hours. Her results are shown in the table below. Plot the data on the grid to investigate the type of growth pattern. All right, so number of hours was 0. She had 50 bacteria. After 1 hour, there were 75. After 2 hours, 112. 3 hours, 169. 4 hours, 253. And 5 hours, there were 380. All right, so we know we can connect these because you could have, after 0.47 hours, there'd be so many bacteria. So these are a continuous function. From the list below, select the best alternative for the type of growth pattern exhibited by the data. All right, so if you recall, let's talk about each of these. A linear function, well, that's any straight line, goes forever in both directions. A quadratic function could be a U-shaped parabola that opens up, or it could be a U-shaped parabola that opens down. These are the types of quadratic functions we studied in grade 11. They are also some that open right and left. Exponential function, well, we've studied lots of those, right? They can look like that. That's exponential growth. And logarithmic functions, well, we studied those, and those seem to look like that mostly. So based on those 4 statements, which one does this look like? Well, it looks most like exponential, but it could maybe be half of a quadratic one. Might just be one leg of a quadratic one. It could maybe be a different kind of logarithmic one, but we haven't seen that yet. So we have to use regression now to figure out exactly which one it looks like. Although the points above appear to form an exponential pattern, it may not be possible to find an exponential function which passes exactly through each point. The statistical process of regression will determine the best possible exponential function in this form, which will get as close as possible to all the points on the graph and all the data points we used. The regression features of a graphing calculator will be used in this course to determine the equation of the best possible exponential function. The next 2 pages describe the process. Note the graphing calculator can also be used to determine the best possible linear, quadratic, exponential, or trigonometric function depending on the pattern exhibited by data points. So you could go through and you've got all that data on the next 2 pages. You've got all the information of how to do it. I'm just going to go along and explain to you how to come up with the equation that best models this data. And we're going to make the assumption right now that it's an exponential function. All right. So you've got this page open on your notes. Let's go to your graphing calculators and let's follow along. Get to your home screen and clear it. Step 1, hit your Stat button. And we're going to edit our list. So it's already in edit. Just press Enter or the number 1. And your lists may have lots of data in them. That's fine. Let's go to List 1. Go up until List 1's highlighted and press Clear Enter. And that'll clear a list for you. All right. Up to List 2, Clear Enter. And you can clear as many lists as you want. We probably won't need more than the first 2 lists. Now in List 1, let's type the number of hours that we had from Simone's data. So she studied the bacteria for 5 hours, so 0, 1, 2, 3, 4, and 5. That's in List 1. In List 2 were the actual number of bacteria that occurred after that. So at time 0 she had 50, and then 75, 112, and so on. Right, so once you have your data typed into your lists, the next thing we're going to do is plot this data on a grid so it looks just like we have in our workbook there. All right, so let's plot the data. So if you go second y equals, you get your stat plots. So you've got 3 different stat plots, plot 1, 2, and 3. We're on plot 1, so let's just press Enter. Right now you can see plot 1 is off because it's highlighted. We want to turn plot 1 on, so simply press Enter, because on is highlighted. Use your down arrow, and you've got a bunch of different types of graphs we can plot. We're going to just use the one that's highlighted right there, the scatter plot. That's fine. Our X list, in our notes it says the number of hours should be our X list. Our X list, we put the number of hours in list 1. That's already there. And our Y list, the number of hours should go, or the number of bacteria should go in list 2, our Y list. And here is just the kind of mark we want, whether it's a box or a plus sign or a dot. The last thing we're going to do is change our window setting. So make sure you have a window setting that makes sense. So the number of hours should go from 0 to, like in our notes, it's 6. Maybe just so I can see the y-axis, let's go from -1 to 6 by a scale of 1. And the minimum bacterial growth, again, just so we can see the x-axis this time, let's go -50 to 400 by a scale of 50. So now if we hit graph, we see our stat plots, but I've also got a couple y equals equations in here, so let's clear those off. So there you go. Those are the plots we graphed in our notes. So now we're exactly where we are in our notes. But how do I know what the equation that matches this data is? Well, I've got a bunch of the data in our lists. So all you have to do is go back to your home screen. So second quit. Now hit your stat button and go over to your calculate menu right there. So use your right arrow to get to your calculate menu. And in this menu, we scroll down until we find there's linear regression, quadratic, quartic, or cubic and quartic. Another linear regression in a little different form. There's a natural logarithm. There's our exponential regression. So press enter. And now you have to tell it what data, where to find the data. If you don't tell it, automatically assumes that list 1 is X and list 2 is Y, but let's tell it just to make sure. So you hit your second function button, and above the number 1 is list 1. Then your comma is above the number 7. And second function list 2, which is above the number 2. And now we want to store the data somewhere. So hit a comma again above the number 7. And let's store this into our Y1 feature. So hit your variables button and scroll to the right and go to your Y variables screen. We want to put it as a function, so press enter, and in Y1. So what we've just told the calculator to do is do an exponential regression on lists 1 and 2, where list 1 is my X coordinate, list 2 are my Y coordinates. And once I've come up with the equation, I want you to store it in Y1 on my graphing calculator. So that's what we've told the calculator to do. So when I press enter, I'll get the equation in the form a times b to the exponent x. All right. Now, if I press graph, we'll see how close it matches the data. So because it was in Y1, it's graphing that equation, and it seems to be going through all the points pretty nicely. If you hit your y equals screen, you notice that the equation's listed in Y1. So that's exactly where we wanted it. Didn't have to remember all the decimals, and we didn't have to round it, so we get it to that point. All right. Now, how do I know if this is the best equation? Well, they've got a diagnostic feature on the calculator. So let's go back to our home screen and go second catalog. That's how I find it. And you see the alpha cursor in the top right. That means all the letters are now in play above our buttons on our calculator, and we want diagnostic, so I'm going to hit D. That just lets me skip through all the A, B's, and C's, and I want to go down until I see the diagnostic tool, which is right about there. So I want to turn the diagnostics on. Right now they're off. If I turn it on and press enter, it says, yep, great, I've now done that. If you go second enter, it remembers your last calculation. go second, enter again. It remembers it a couple back. I think it remembers the first 10, your last 10 or maybe 20 entries. So there's my exponential regression for lists 1 and 2. I'm going to store it to y1. I'm telling it to do the exact same thing, but now my diagnostic feature is on. And look what a different screen we get. We get the same equation. A is 49.947, B is 1.500, and so on. But now we have these r squareds and r's. All right. So the r value will tell us how close we are to being exactly matching the data. And the closer this number is to 1, the closer it is to matching the data perfectly. So 0.99996 is a pretty good match. And as you saw with our data, the equations seem to go right through all the points. All right. Now the only thing they want us to do in the book is maybe write this equation down. So let's go back to our notes and maybe write the equation that matches this thing the best. Y equals 49.9, we'll say, times 1.5 to the exponent x. That seemed to be the graph that matched the data pretty well. All right. It seemed to go through these data points almost perfectly. Had an r value that was almost 1. All right, now let's try another one. Let's go to page 228 and try class example 1. So in class example 4 from the previous lesson, we discussed carbon dating. The percentage of carbon-14 remaining was expressed as an exponential function of the age of the organic remains. Since a logarithmic function is the inverse of an exponential function, it's possible to switch the variables and write the age as a logarithmic function of the percentage of carbon-14. The table below shows data for 5 recently discovered fossils. Create a scatter plot using a graphing calculator to confirm that a logarithmic function is an appropriate model for the data, and then do a natural log regression. So let's type this data into our calculator. So let's clear our home screen. Let's go to Stat, edit the lists. So in list 1, clear enter. Over to list 2, clear enter. And our notebook tells us that list 1, going to be our x coordinates, will be the percent of carbon-14. So type those numbers in, 95, 79, 68, and so on. 38, 27. And list 2 should be our y coordinates, and they will match up with the years based on the carbon remaining. So 425, 1950, and so on. Beautiful. Create the scatter plot. So go to your y equals screen and clear off the equation we had. Go second y equals. Scatter plot's already on, but just make sure it's on's highlighted. Great, we've got a scatter plot. We're putting in list 1 and list 2. X is list 1, Y is list 2. Beautiful. We'll use the squares again. Now we need a window that makes sense. So my X window this time is percentage of carbon-14. So the minimum percentage is 0 and the maximum percent is 100. You know, maybe we'll go by a scale of 10. And our Y's are the age in years. So when there's 100% remaining, the age is 0. And when there is, looks like 27% remaining, there's 10,000. So maybe we'll go to a Y max of maybe 30,000. And let's go by 1,000 as a scale. So if I graph it, we get those scatter plots. All right. Part B in our notes now says use the natural logarithmic regression feature of a calculator to determine a function in the form y equals a plus b natural log x. It'll model this data and use the integer values for A and B. All right, so let's do that. Second quit, back to our home screen. Hit your stat function, over to calculate, go down until we see natural logs. So number 9 is our natural log regression. Press enter. Again, I want my X list to be list 1, so second list 1, comma above the number 7, second list 2, comma above the number 7, and I want to store this in my Y variables, Y1, so hit your variables button. To the right, go to Y variables. Yep, it's a function number 1, and I'll store it in Y1, and then I've got it stored in my calculator. All right, so now press enter, and it'll find the natural log regression equation. And there it is, y equals a plus b to the natural log x, where a is 38,067.2557, b is negative 8265.798. And look at our r factor. That's, again, the r squared is even better, is really close to 1, so that's what we're trying to find. That means this should match up really nice. If I hit graph, look at how nice that matches up. It almost hits every point. So that seems to match up with the data we've got pretty nicely. So in our notes, it wants us to use the natural log, write down the equation using a and b values as integers. So let's round it. So this equation should be y equals, our a value was 38,067 as an integer rounded, minus our b value was plus negative, so minus 8,266 times the natural log of x. All right. On the graphing calculator, display the graph over the scatter plot. We did that. Use the graph in C to answer the following questions. Part 1. A bone fragment with the carved image of a mammoth was discovered in the southern U.S. state of Florida in June 2011. Estimate the age of the bone fragment if there is 20.3% of carbon-14 left. So x is the amount of percent, so x is 20.3%. Find the corresponding age to the nearest 1,000 years. Let's go to our graphing calculator. We know what x is, so hit your trace function. Now you have to be careful because we've got plots as well. So plot 1 is here now. So use your up arrow to get to y1, which is the equation that matches the plot data we've got. So my trace feature, I want 20.3%. So when x is 20.3, what's the age? Well, the corresponding age turns out to be 13,182.071. So to the nearest 1,000 years, that would be 13,000 years. So y was 13,182.07 and so on. So the actual age is 13,000 years to the nearest 1,000. And part 2. If the skeleton of a bison is about 10,000 years old, what percentage to the nearest whole number should be remaining? So now you have to go y2 and type in 10,000 years, find that point of intersection, and list the corresponding x coordinate. So go to your y2 feature. In y2 we want to type in 10,000. Hit graph and we'll see that line show up, and we want to find that point of intersection. So second calculate, point of intersection number 5. Hit enter twice, 3 times. We don't need to make a guess. And it looks like it's about 29.832. 29.832 is our x value to the nearest whole number. We would say there is 30% carbon-14 remaining. All right. So you compare these answers with class example 4 from the previous lesson. You go back and look and you'll notice that they're the same. Okay, so you've got your work. Away you go.